Okay, this is 7.2 sectors of circles, and the objective will be to find the arc length and area of a sector of a circle and to solve problems involving apparent size. This is really cool stuff. So first, arc length. Well, arc length is just the length of an arc somewhere along a circle. So this right here would be an arc length. And we use an S to represent arc length of a circle, of the arc on a circle. A sector. A sector is nothing more than a piece of pie in layman's term. So a sector of a circle, let's get the official definition for pre-calculus. The region bounded by the central angle. So this angle right here would be a central angle and the intercepted arc. This is the intercepted arc, and that piece of pie is a sector of a circle right there. So let's say that is 60 degrees. I'm just going to see where you guys are right now. Can you guys convert 60 degrees to radians and give me an exact answer? 60 degrees equals, now picture your unit circle. And you see this right here? That 60-degree terminal ray is the equivalent in radians of pi over 3. Get used to those conversions. It will make your life so much easier. For instance, on the next problem. Oh, by the way, there's the intercepted arc right there. How about a radius? Well, let's throw a radius in here. This looks to me like, I don't know, 12. I'm kidding, that could be anything, but let's throw a 12 there. Okay, so with that diagram, let's answer some questions. So first, 60 degrees. I want to use this central angle right here to come up with the length of this arc S right there. What is that? All right, well, that would be a fraction of the entire circumference of the circle, and I think you know what that fraction might be. My central angle is 60. And what is one complete revolution in degrees? 360. So wouldn't 60 over 360 of the total circumference give me the exact length of this arc right there? So what's circumference then? Go back to geometry, 2 times pi times the radius. Or pi times diameter, but we have a radius right there, so why don't we use it? So let's go 60 over 360. You don't have to, because you're going to use a calculator probably, but I'm going to reduce that to 1 over 6 times 2 pi. And what is the radius of this circle? It's a 12. All right, well, let's clean that up. So 6 goes into 12 3 times, or 2 times, excuse me. So that would be 4 pi. And again, I don't have to write this, all right? But yeah, I do actually here. Arc length, so that's this distance, and they didn't tell me what unit that is, so I'm probably going to say 4 pi units. Oh, and I didn't even put the units there, but I should have. All right, anyway, let's do this another way. Arc length equals theta times radius. Now, I can only use this formula for arc length if my central angle is in radians. So S then equals, and that central angle is 60 degrees, and you recall 60 degrees would be how many radians? That'd be pi over 3. There we go. Times the radius, which is 12. And I don't know, 3 goes into 12 4 times, so that's 4 pi. So either way, and both of those should say 4 pi units. I'm getting sloppy there, I'm sorry. Okay, now area. We're going to use the same concept. You see that central angle of 60? Think 60 over 360. 60 over 1 complete revolution, 360 of the total area. So that would be 1/6 of the total area of a circle, and the total area of a circle is pi r squared. Pi, what's the radius? 12. All right, so let's clean that up. 12 squared would be 144. And does 6 go into 144 evenly? I think it does. Let's think about that. 6 would go into 60 10 times, so 120 20 times, and then 24 more. I think that's a 24. Let's check my arithmetic though. Hey, there you go. So 24 times pi. Good. See, I'm not that old. Okay, and now that is an area, so that should be square units actually. Man, I can't believe I'm not putting my units on this. I'll make sure I do when I present this though. Okay, all right. Formulas for the arc length S and the area K of a sector with central angle theta. All right, put 5 stars on this page. Okay, there's our typical sector of a circle right there. You see the central angle. The area of that sector we call K, and S is our arc length right there. Okay, now here's your formulas for both arc length and area. Okay, if theta is in degrees, we use formula number 1 for arc length would be, again, central angle theta over 360 times the entire circumference of that circle, 2 pi r. And area K of the sector would be the same fraction, theta over 360 degrees, times, and then we have area pi r squared. Now, if theta is in radians, this is the arc length formula we found in our last lesson, and that's going to be, I usually call this theta times r, but right here they call it r times theta, and I think they want to make a conversion a little easier for you. Because look at 2a over here. Area of this sector, if we're in radians, all right, well, that's going to be 1/2 r squared times theta. Okay, that is the area of this sector if our angle theta is in radians. All right, now watch this, you guys. Since we just said arc length is r times theta, do you see a factor of r times theta right there? We can simplify this formula. We can rewrite 2a, k equals 1/2 r squared theta as 2b, k equals, well, let's have a 1/2 r. And then we have another r theta right there as s, so that would be 1/2 rs. Oh, I like that formula. Okay, let's use these formulas. All right, so a sector of a circle has an arc length 6 centimeters. Let's put that in our diagram right there. And an area of 75 square centimeters. And there's our 75 right there. Okay, find its radius and the measure of its central angle. All right, so we can use one of our formulas, and let's think about what we have here. We have an area K and an arc length S, and we're looking for this radius right here and the central angle. So can I use that 2b that we just talked about? K equals 1/2 radius times arc length. And now let's plug in what they gave us. So K, they said, was 75. And the arc length they told us was 6. And now let's solve that for the radius. So 6 divided by 2 would be 3. So 3 times r. Let's divide both sides by 3 to get r equals 75 divided by 3. And that would be 25. And that's 25 centimeters too. Hey, I've got the units in there. Okay. Now, how about the central angle here? All right. Well, arc length is, and again, what are we going to do this in? Well, are we going to use radians or degrees? How about we use radians, r times theta, or theta times r if you prefer. All right, so let's plug in what we know. So, what's the arc length? Oh yeah, that's 6. And we just found that the radius was 25. So theta then would have to equal 6 divided by 25. All right, and now again, that is in radians, so equals, wow, well, 6 divided by 25, that's not going to be a whole number or anything, or a reduced fraction there. It must be, let me punch this out. 6 divided by 25. 6 divided by 25. Oh, I'm getting 0.24. I thought that would be an uglier decimal. 0.24. And again, if I don't put anything and my answer is a decimal, it's assumed that this angle theta is in radians, but for teaching, I probably put radians right there. But if you just wrote 0.24, that would be appropriate. Now, if your angle is in degrees, you need the degree symbol. All right, so you answered the question. Good. Degrees, hey, question mark. So this is just practice from 7.1 then. Let's convert 0.24 radians to degrees. So theta then would equal 0.24, and let's multiply that by 1, but let's write that 1 in the form of we want our answer in degrees. So how about we take a fraction and put a 180 degrees in the numerator, and then in radians that would be pi. 180 over pi is 1, so we can punch that out on the calculator, and this one we're probably going to have to round there, so let's just punch it out the way we see it. 0.24 times 180 divided by second pi, and I'm getting 13.75098708. I rounded that to 14. Wow. I usually don't round to the nearest whole number. I was expecting to do a 13.75. And again, anyway, 14 what? Degrees. There you go. Okay, well, what else do we have to go here? Oh, apparent size. So when there is nothing within our field of vision against which to judge the size of an object, we perceive the object to be smaller when it is farther away. You all know that. So here's a great diagram of what apparent size is all about. See that eyeball right there? Okay, now watch. For example, the sun is much larger than the moon, but we perceive the sun to be about the same size as the moon because the sun is so much farther from Earth. All right? Thus, how big an object looks depends not only on its size, but also on the angle that it subtends at our eyes. The measure of this angle is called the object's apparent size. So that's an example of the apparent size of something like the sun or the moon, something that's really far away. All right, the angle that it subtends with our eyes is something as small as 0.01 degrees. So how is this used? All right, we can do some really cool problems where we're asked to do something like, oh, I don't know, Jupiter has an apparent size of 0.01 degrees. When it is 8.10 or 8 times 10 to the 8 kilometers from Earth, so there's my eyeball right there, all right, and we're talking 8 times 10 to the 8th kilometers from Earth. So this radius right here, I'm going to say is going to be 8 times 10 to the 8th kilometers from Earth. Find the approximate diameter of Jupiter. Well, do you see this arc length right here? Could that be used to approximate the diameter of Jupiter? It's actually a pretty close approximation. It'd be a little bigger than the actual diameter, but this is what this is used for. So let's approximate. So the diameter is approximately the arc length of a sector. So theta in degrees. Let's go ahead and use the geometric method here. So we're going to go arc length then is, and we've got our central angle over 360, 0.01. Don't go in general right here. Theta over 360 times the total circumference of, in this case, the distance around the equator of Jupiter, which is 2 pi r. Okay, equals, all right, now let's fill in what we know. So we have theta, the apparent size is 0.01 over 360 times 2 pi times, and what's the radius again? Remember, our eyeball is right there. That is 8 times 10 to the 8th power. And now let's just carefully punch that out. On 0.01 divided by 360 times 2 second pi times 8 times 10 to the 8th. Let me double check everything. 0.01 divided by 360 times 2 pi times 8 times 10 to the 8. Yep. And I'm getting 139,626.3402. And they said, did they tell me what the round to? They did not. So how about we round that to the nearest thousand, because this is a really rough estimate. So that's about 140,000 kilometers. 140,000 kilometers. And that is how you do an apparent size problem. That's cool stuff. All right, I'd like you guys to do page 264, 1, 3, 7, 8, 11, 12, and 15. You have the odd answers in the back of your book, and I'll post the even answers in Google Classroom. You all have a great day, and give me an email if you have any questions. Thanks. Bye-bye.